Hi everybody, welcome to Calculus, Part 3 about limits. We are talking today about continuity and one-sided limits and also infinite limits. So briefly we just want to take a look at graphs of functions or three conditions where we know that the function is not continuous, and that's what we're looking for, continuous function. So first we have a place where there's an open point on the function. This is where the function is not defined at x of c, or x equals c. Okay, that doesn't mean there is not a limit going towards c, but there is not one at c. The second one here, this is a non-removable discontinuity, or what we were calling a jump discontinuity. The function or the limit of the function doesn't exist here because as you're approaching from the left and the right, the limits are two different numbers, and we know that that means that the limit does not exist. And on the last one, the limit of f of x exists at x equals c, but it's not equal to the actual function. It's not in this place, and so therefore there is another removable discontinuity. So the function that is continuous on the interval has to be the opposite of those discontinuous things. It has to be defined at x equals c. It has to be continuous on every point in the interval, and or it has to be continuous for the entire number line. And here are the solutions for those limits. The limit of -1 as you approach from the left is 4. As you approach from the right is 4. So the limit of f of x as x approaches -1 is 4. If we're looking at the limit as x is approaching 2, the limit coming from the left is -1. The limit coming from the right is +5. So the limit for the function at x is 2, as x is going to 2, does not exist. There is a jump discontinuity there. Okay, it's at this point that we just introduced the intermediate value theorem. So what this is saying is that on a closed interval, if you were to have some values of m, multiple values of m, that meet the graph at multiple places, all it means is there has to be within the interval, then there has to be values of c that are also within the interval of a and b. That's really all that this is saying. We use this when we're trying to locate zeros of a function on a continuous closed interval, and we will be putting this to use a little later on. The other kind of behavior we want to talk about is limits at infinity. We say that this occurs when there is unbounded behavior, such as when you see a graph like this where the limits go off along an asymptote. And so we're going to talk a little bit about how to find the vertical asymptote and what that means to us regarding the limits at infinity. Now we have to talk a little bit about how to find a vertical asymptote. And so we're talking about looking for a place where as x equals c, the numerator is a non-zero number and the denominator is a zero number. Okay, and if that is the case, then a vertical asymptote exists. So in this particular function, at x equals 2, we have a place where the numerator is a non-zero 4 and the denominator would be 0. And so for this function, there is an asymptote at x equals, there's a vertical asymptote at x equals 2. So now what we do with that is take the limit coming from the left and coming from the right of 2 and see what we get. So when we take the limit of the function as x is approaching 2 from the left-hand side, we get negative infinity for the limit. And as we take the limit of the function as we're approaching from the positive side, we have positive infinity. So if this were 2 on the line, we would expect to see something going up this way and something coming down this way. Probably, that wasn't really a good spot, probably down here, if you know what I mean. So I've left a problem for you to try. I'd like you to see if you can determine if there's an asymptote, and if there is, find the limit from both sides. So when you look at the function and you try to decide if there's an asymptote, I can see that if x equals -1, that's what will make the denominator 0. So when I substitute that in, I get a 0 in the denominator, and I get a non-zero number in my numerator, which tells me there's an asymptote at x equals -1. So now if I take the limit of both of these functions, I will see that the limit coming from the left is negative infinity, and the limit coming from the right is positive infinity. So the last thing I want to look at is some properties of infinite limits. I've given you a list on your study guide, but we're really only interested in the first one for today, and that is the sum and the difference of two functions. So the first part of this is what I put up here, and that is if you're finding the limit of one function is infinity, and the other one is, we're calling it L for a limit, as in an actual number value. If you have this relationship and you're putting functions together, there are ways that we can manipulate the equations to find these things out. So we're kind of combining the work that we did earlier in this chapter, and that is if we're finding the limit of the sum or the difference of the functions, and one is infinity and the other one is a number, then you're going to say that the limit of the sum is infinity. So if I gave you the limit of the function 3 plus 1 over x squared, I can split these. We did this earlier in the chapter as well. Remember, we said if you have two parts to the function, you can split them and take the limits of each and then put them back together again. And that's just what I'm doing here. I'm splitting them. I took the limit of 3, which is 3, and then I took the limit of the other part of the function 1 over x squared, which would be 1 over 0, which is indeterminate, and so therefore the limit would be infinity. So according to my rule above, this says if one of my functions has infinity for a limit and one has some number value, then the number, the value of the function when they are combined would be infinity. I wanted you to just see this. We're going to do a little practice on this in class, and that's all I have for you for now. Thank you.